So an example now is to determine the load P, where load P is an applied external load on the structure. And we're going to assume that AB is made of steel. And so what's the maximum load P such that the frame doesn't buckle? So a couple things to jump out at us is that we need to deal with units in these problems. We've got cross sections in millimeters, we've got length in meters, got gigapascals. So units will have to be assessed, and the effective length up here in the problem statement says it's pinned for the YY axis. So LEY is going to equal 1.0 times the length. That's for pinned. And it's fixed about its ends for X buckling. So that factor is 0.5, and those numbers can be found right on the bottom of your equation sheet as well. So we just want to keep track that for member AB, so the member that is in compression in this two-member frame, we would know that P critical is equal to pi squared EI over effective length squared. And again, we're going to need to check the X and the Y separately to come up with the critical buckling load. That's the internal force, and we're going to need to relate that to the external force P. So relating those quantities is going to be done by free body diagram. We've got a frame, we've got pins at B and C, we've got an internal hinge at A. So both members are two force members. So when I come through here with a blue saw and cut it open, I end up with a free body diagram of A. And so we've now cut that member, we've cut the vertical member horizontal, we've got the applied external load, and inside here we've got the internal force in member AC, and here the internal force in member AB. So just kind of looking at that free body diagram again, right, we notice the geometry of this force here would be a 3 to 4. And so it's kind of slick here. Instead of summing forces X and Y, which we'd be able to do in two equations to find the internal force AB, we can just sum moments at point C, which would be sitting right down here. We sum moments, we have to get 0. And so our equation would look like P, which is the external force, times 4 meters, plus the internal force, PAB, times 3 meters, has to equal 0. So we can kind of look at the geometry there. That would be the lever arm for the internal force here. That's the lever arm for the applied external. And so just solving that, we would have that PAB is equal to minus 4/3 P. All right, so moving forward, we need to check buckling about both the X and the Y axis. So P critical about the X axis would equal pi squared EI about the X axis divided by LEX squared. The other one we'll have to check is P critical about the y-axis, which would just equal pi squared EIY divided by LEY squared. So we really have all the equations that we need here. What we're going to end up doing is comparing P critical about the y, P critical about the x. The smaller of those is going to be assigned for the internal force AB, and we'll be able to then solve for the external force P. All right, so we got to grab some more values here. We've already laid out the effective lengths, so we're going to need to play with the length also. So we'll go back up here, and also we've got the cross-sectional properties that we're going to need for moment of inertia. So So we'll grab some of those here. The actual length of the member is 6 meters, which would equal 6,000 millimeters. We need some moments of inertia. Moment of inertia about the x-axis would be 1/12. There's the x-axis, 1/12 the base, which was 50 millimeters. The height, which is 100 millimeters, and that's going to be cubed. And if we calculate that, we would get 4,166,667 millimeters to the fourth. Moment of inertia about the y-axis, which would be sitting in the vertical direction, 1/12 the base, which is the side parallel, which would be 100 millimeters times 50 millimeters h cubed. Multiply that together, we would have 1,041,667 millimeters to the fourth. We'll also have to play with E, where E is equal to 200 gigapascals, and a gigapascal is a kilonewton per millimeter squared. So we've got all the values that we need, and so plugging all of those in and doing the math, you'd end up with P critical about the x-axis, which would be 914 kilonewtons. P critical about the y-axis would be 57.12 kilonewtons. So this is going to govern. This is the smallest of the two buckling loads. So we're now ready. The applied external load P, which would be equal to 3/4, right, flipping that to the other side. Members in compression, and so simple multiplication out the other end would tell us that the critical buckling load would be 42.8 kilonewtons. And they gave us in the problem one more piece of information. They gave us sigma yield, which was equal to 360 megapascals. So now we have the ability just to check the material. And so P over A, the normal stress, would be the internal force in member AB, which we know is equal to 57.12 kilonewtons, dividing by the cross-sectional area. Do your units, you'd end up with 11.42 megapascals, which is clearly less than the yield of the material. So we've got buckling that has occurred before the material has yielded. Sigma calculated is less than sigma yield. Therefore, the applied external load is going to be 42.8 kilonewtons, again found in the buckling analysis.